Welcome to lecture number 7 in the Finite Element Method course this semester. And today, as you see here on my slides, will be the discussion of the last ingredient for our final discretization scheme. And this will be numerical integration. So in those last lectures and weeks, we have discussed discretization for the domain, so creation of the grids. And then we have derived weak derivatives and weak formulations. Then we talked about local polynomial spaces, the global piecewise polynomial spaces. And then at the end of lecture number 6, we have seen that we can essentially put all those ingredients together, but there is just one thing left missing, and that is the actual computation of those integrals over the reference cell. And that's what today will be all about, so that after this lecture we are able to put our final scheme together and assemble our finite element system and actually get some solutions. So let's see what's on schedule for today. We start with a short introduction as usual, a recap from last lecture, what we have and what is left to do. And then we talk about integrals and why they are slightly problematic to compute, especially on the computer. Then what's special about integrals in FEM. The second chapter of today will be the general concept of quadrature. So we talk about integration versus summation, so how we get from that abstract mathematical object of an integral to a discrete object, so a sum. Then we talk about transformation, so that we can derive our quadrature rules only on certain simple domains and then be able to transform them, just like we are doing it with the basis functions in FEM. Then the part of exactness, so is it good what we're doing here in the sense that how do we measure the quality of approximation of a certain quadrature scheme? And then that last part, that's very interesting and very, probably new to some of you, the optimal quadrature, so the construction of, in a certain sense, optimal rules for numerical integration. We start by doing this in 1D with the classical Gaussian quadrature. And then we transform this to 2D and talk about Gaussian quadrature in 2D on rectangular domains, which is not super relevant for our finite element applications in this course, but in general is the natural transfer of the concept of an interval in 1D. And then in the end, we talk about a Gauss-Type numerical scheme for integration in 2D that's specifically well suited for triangles. So we take those ideas of Gaussian quadrature and then we apply those ideas on triangles and actually try to derive optimal quadrature rules there. So let's see how this all works out. Let's start with the introduction. What you see here was the last slide that we had in the last lecture, where we have recapped that all those ingredients we need for the load vector and the stiffness matrix are essentially almost there. So we have seen that almost all of those ingredients can already be computed from the things we have discussed before. And the only thing that was left missing was this red box with the integral over our reference cell. So, concluding from this, the agenda for today is discussing how can we do integration over the reference cell. The general key problem here is if I have a given integration task, so I want to compute an integral of some function over a certain domain T, and I want to do it on a computer, how can I do it? And that's in general a non-trivial question. So even though you might be used to the case where in 1D you can simply compute those integrals by hand analytically, So like using the fundamental theorem, meaning that, well, let's say you want to compute an integral over some interval from -1 to 0 for the function sine of x. And then you say, well, this primitive, so the antiderivative here of my sine function, that's just the cosine function, or minus the cosine function. And then I can say, well, using the fundamental theorem, that's just -1 to 0 for the cosine function. So that's minus cosine of 0 minus, so plus cosine of -1. And that's, well, something. Okay? But in general, it's not that simple. So this antiderivative, the primitive, is difficult to compute, especially in multiple space dimensions, and it might not even exist. So for example, if you consider these f of x in the e to the power of minus x squared half, known from the Gaussian probability distribution, that function can be proven to not have a primitive. So it's simply not doable. And even if it's doable, it requires symbolic computations using Mathematica or SymPy or other symbolic tools, and that's very inefficient, and it's not what we want to do. So for our high efficiency tasks of using finite elements, this is simply not well suited. So we need something better. And that's what we're going to discuss today. One particular thing we need to mention is that FEM, in a sense, is a bit of a special case. So, as you have seen in the last lecture, when you want to derive the formula for the stiffness matrix, you stumble across those types of integrals, like printed here. So those integrals are often involving basis functions, so gradients or function values of basis functions over certain cells. And why is that special? Well, let's see. Those basis functions that we have seen in the last lecture, they are never given in a closed form. So you never have an analytic description like phi j, so this global basis function is sine of x, let's say. That's never happening. The second thing is that FEM in general is only an approximation, right? We know that from the start, the FEM solution that we're getting is not the exact solution of the system. And the last thing, if we wanted to actually analytically describe T, our integration domain, so some cell or something, that totally does not match our data structures of storing cells and points, because, well, analytic descriptions are always kind of difficult if you have data structures involving only vectors and matrices. So with all those things combined, we don't have a closed form representation for the integrand. The whole thing is an approximation, and we cannot really analytically describe our integration domain. That leads us to the conclusion that we don't need analytic computations for the integral values. We don't need symbolic computations, which are inefficient. We only need to approximate our integral roughly as good as the method in general is. So if your numerical scheme of finite element methods is an approximation, the only thing you need to do when talking about integrals is approximate them as good as the method in general is, because otherwise there is no use in computing integrals exactly with zero error if the thing that you are computing is not the exact solution anyways. Now that we have found out that we want to generate a numerical scheme for integration, we want to discuss what that in general means. So let's talk about the general concept of quadrature. And that whole thing, it can be summed up in this simple equation here, or approximation. the whole concept of quadrature comes down to taking an integral expression and approximating this using a summation. And it is in particular a weighted summation of function values. So what does that in general mean? Well, it means that if you have, let's say, you have an interval given and you want to integrate a certain function over that integral, then you will not compute that integral exactly, but you will only evaluate your function at certain points. Let's say those 3 here. So I take my function values at those points. I sum those function values up and assign them certain weights. Let's say 1/2, 1/3, and 1/4 maybe. But we will see later on how this makes sense to choose them. So the general concept is go away from the abstract mathematical concept of an integral and towards a simple thing like a summation of those weighted function values. Because that's something we can do on the computer efficiently. So we can evaluate a function at certain points. We can do this scalar multiplication here, that's also no problem, and then we can sum it all up. Okay, so that's all of those tasks are easily and efficiently doable on the computer, and that's why we chose to go this way. Okay, what does that in particular mean? Or let's talk about the notation. Those WKs here, those factors are called quadrature weights. Because as I said, they kind of weigh the individual contributions, so they balance how important a certain function value is for the whole computation. And then those xk's here are quadrature points, so those are the points that are of some interest to us, where we want to evaluate our function, and that's kind of the representation or the representative points. And if you have a set of weights and points, that gives you a quadrature rule. So it's important to say that a quadrature rule always consists of those 2 ingredients. You have quadrature weights and you have points. So it's never a rule if you only have the points or only have the weights. You always need both, because otherwise that rule is not uniquely defined. So I need to have that WK and I need to have that XK. But of course there is questions. So the first one, the most urgent one probably is, how do we choose WKs and XKs in a good way? So how do you choose the points where you want to evaluate your function, so those representative points, and how do you choose the corresponding weights that balance those individual contributions in a good way? And the second question that directly comes afterwards is, what does good even mean in this context? So how do you measure the quality of an approximation of the quadrature scheme? And then what's also interesting is, if this, you can already probably assume that choosing points and weights in a good way is not super trivial. So it would be kind of problematic if we would have to derive a specific rule for every integration domain T. So the last question is kind of, do we have to do that individually for each cell, or is there something better we can do? And that last question is the first one we're answering here, and that simple keyword that I'm giving is transformation. So the answer to the question is no, we don't have to define or derive an individual quadrature rule on every single type of cell. Instead, we define the quadrature rule only on some simple domain, which we call T hat. And we find a transformation that maps between this T hat and different other integration domains. And then we transform the points and weights using an integral transformation. And while I've said this probably most of you have been thinking, well, this does sound kind of familiar. So this does sound like the whole stuff that we've been doing in FEM with basis functions and so on. That's the same motivation we talked about. We want to define our basis functions only on a simple domain and then find a transformation, which we call the reference map, and then we transform the stuff. And that's exactly what we're doing here. And that's also one of the reasons why numerical integration is such a perfect match for FEM, because you can use those previously derived reference maps, for example, and put them to another purpose in transforming your numerical integration schemes. Let's look at this a bit more in detail. So if you have an integral given over a certain domain T of some function, and you want to transform it back to some other domain T hat, so our simple reference, you can always have in your mind that just like before, T hat is that simple reference cell and T is some other triangle. And then you have given your function ft mapping from here to there, such that if I would apply ft to the whole domain T hat, I would simply get T. And then that integral transformation theorem states that, well, if you want to transform your integral from T to T hat, you have to include this determinant of the Jacobian of ft, which is the area scaling factor, so the difference in areas. And then you additionally simply evaluate f at transformed points. Okay, so that's always the two ingredients when talking about integral transformation. You transform the points and you rescale the area. That's something we talked about in the last lecture. And now, well, if you have a quadrature rule on T hat that approximates integrals on T hat, then I can, of course, use that now and simply plug in my points and weights. So my points are here and there, and the weights. And that gives me a numerical integration scheme on my original domain T. Because I can always say that, well, if I have an integral on some cell or on some domain T, which can be transformed to the domain T hat where I have my quadrature rule, then I can always go that way. So that's always the same procedure. Transform the integral to that domain where you have the quadrature scheme and then apply that scheme there. And if you look at this in detail, you see that it comes down to the same shape that we always required from quadrature rule. So you again have certain factors here. Those WKs are formed by A, those weights that you have on the reference, and this determinant as an area scaling. And those new points where you evaluate your function f are given by the transformation of the points on the reference. And that, again, if you define your wk and your xk like this is just the usual form of a quadrature rule. So that's wk times f of xk. So bottom line of this is you don't need a particular quadrature rule for every type of cell T or every type of domain, as long as you have one rule on a certain reference and you can transform your other cells to this one using a transformation. So in FEM applications we are always good to go, because there we always have those reference maps for every single cell in the grid, so we can do this no matter what. Let's look at an example of this. So if you have if you know the trapezoidal rule, which is very famous, or probably the simplest numerical integration scheme that is taught in every numerics basic course, that tells you that if you have an integral on the interval from 0 to 1, then you can simply approximate this by evaluating your function at the left boundary point and at the right boundary point, so at 0 and at 1, and then you divide the sum of them by half. So you take them by half, so in a sense forming the average of those two values. Now, that means if you express it in the standard way of writing down a quadrature rule, that you have two quadrature points. The first one is 0, the other one is 1. And you have two weights. They are both weighted 0.5, because if you write this in a different way, this means I can say that 0.5 f of 0 plus 0.5 f of 1. Okay. And now let's see what happens if we go to another cell, in this case another interval. So let's say we want to transform that whole stuff to the interval from 7 to 12. That is completely randomly chosen. What happens here? Well, the first thing we need is the computation of our reference map. And it's easy to see that if you define your reference map in this way, it actually maps from 0, 1 to 7, 12. Because if you plug in the number 0, this gives you 5 times 0 plus 7, that's 7. If you plug in 12, if you plug in 1, that gives you 5 times 1 plus 7, that's 12. So that actually works. So this is our reference. And then we can form the Jacobian, which is in this one-dimensional case simply just the derivative, and the derivative of this function is the number 5. So this is our scaling factor. And you can already see here that this indeed reflects an area scaling, because this original reference map has area or length of the interval 1, and this interval here has length 5. So you can see that this dft always reflects the scaling of the areas. And then let's look at our transformed points. So we simply use this reference map here, apply it to our original points. So I take this x hat 1, put it in here, that gives me 7. I take that x hat 2, put it in here, that gives me 12. So my quadrature points on the transformed interval are 7 and 12. And let's look at the weights. Well, the weights are simply given by multiplying this area scaling factor with the original weight. So I take this 5 here and take the 1/2 that I have from here, and that gives me 5 over 2. And so my trapezoidal rule on the interval t equal to 7 and 12, so the interval from 7 to 12 is simply given by that average of the two boundary point values times number 5 for the width of the interval. So that's also what the classical writing for the trapezoidal rule is. So if you look at some numeric textbooks, you will always find the trapezoidal rule written in a similar way to this. So an integral from a to b of some function f of x can be written as b minus a, and then f of a plus f of b over 2. So this b minus a is here just the number 5. So if you look at this formula, then you see that this is derived by originally defining a quadrature on a simple reference interval from 0 to 1, for example. and then transforming it. So the next part on the agenda is the original question number 2. How do we measure the quality of an approximation? And you could always try to say, well, I can measure an error, so saying that I form the difference between t, so this actual integral, minus my approximated integral. So saying that this gives me the actual error, and that is a good way of, let's say, a posteriori measuring errors. So if you already have your quadrature rules, and if you could actually compute the integral over f, this gives you a good way of measuring how well your quadrature rule has performed. But the initial problem is usually you can't compute that. So what do? Instead of using this a posteriori error estimation, you go for a priori, trying to find out how good it can perform, and you do this in terms of polynomial integration. So what you try to do when measuring the quality or estimating the quality of quadrature rule, you say that, well, it can integrate polynomials of a certain order exactly. So exact polynomial integration. And let's see what this does in particular. If you look back at our example of the trapezoidal rule, there you could see that, or there it's easy to see that this can integrate linear polynomials exactly. So if you are not talking about the green curve that's underneath, but if you wanted to approximate the integral for a linear function going from here to there, then you can see that my trapezoidal rule gives us the exact values for the integrals, right? And more in general, you can say that a quadrature rule with a certain points and weights, right? What forms them on a certain domain is called exact of order m, so some integer number, if the integral over a certain polynomial function is equal to the numerical integration values for all polynomials up to a certain order. So this m here is the order of exactness. P is a polynomial. So more precisely, the important thing here is that this is not an approximation anymore. Okay? Usually in the definition you always say that the application of my quadrature rule is to say that I want to approximate the integral over f of x, this is important here, by my summation over the quadrature points. But here, when you talk about exactness, it means that up to a certain order of polynomials, so all linears or all quadratic or all cubic polynomials, can be integrated exactly. And as we will see in the follow-up, this is something you can a priori estimate. So you can, when defining a quadrature rule, you can already from the beginning, without computing an actual integral, you can say this rule will be able to integrate linear polynomials exactly. And for example, the trapezoidal rule, which we have discussed before, is exact of order 1 because it integrates linear polynomials exactly. Because if I take the left and the right boundary point of a linear function, everything in the middle is perfectly clear. So let's talk about theory. And we will do this theory only in 1D, because in multiple space dimensions the theory is a little more complicated, but we will see that the application of that stuff is actually not that complicated in 2D. So let's start with theory in one space dimension. So just always talk about intervals. And an interesting lemma is a quadrature rule formed by certain points and weights on some interval is exact of order m if all the monomials, so not polynomials, but the monomials up to order m are integrated exactly. So what is monomials? Those are simply given by a certain power of the variable x. So the monomials are 1 and x squared, x to the power of 3, and so on. So those, let's say, most simple polynomials you can imagine. And I won't prove this lemma here, but in order to get an intuition for the proof, you can think back of the theorem that we discussed in a previous lecture when we talked about the global basis, where we have seen that if I want to check a certain condition on a certain space, it's sufficient to check that condition for all basis functions of that space. And that's the same thing here. So those monomials form a basis for the polynomial space of that order. So it's sufficient to know that these monomials are integrated exactly, then every polynomial of that same degree is integrated exactly. And that proof is also similar to the one that we did in the lecture when we talked about this basis testing, because it again comes down to finding out that the integral is a linear operator, so you can linearly combine every polynomial as monomials and so on. Okay, so in order to quantify exactness, we no longer need to check it for all polynomials up to a certain degree. We only have to do it for the monomials. And that again, just like with the testing with the basis, this is a huge advantage because it's only a finite number of them now. And the second thing, and that's a theorem, that's a bit more difficult to prove. A quadrature rule on some interval with nq points, so with a fixed number of points, can have no bigger exactness than 2 times nq minus 1. So there is an upper limit to exactness. And that kind of makes sense. So imagine that you wanted to construct a quadrature rule with only 1 point, let's say. So you construct a quadrature rule on a certain interval with 1 point, and then let's say you have a polynomial of order 5, so something like this, for example. I'm not sure if that can be written as an order 5 polynomial, but it's probably intuitively clear that no matter where I place my function value, it's not doable to get the exact integral here. So there is an upper limit to this. And, well, if you think about this and look at the numbers, then you see that, well, if I set nq to 1, so I take only 1 point and weight, this gives me 2 times 1 minus 1, so that's 1. Meaning that it should be possible to, so if we can actually reach this upper limit, then this would mean that we can integrate linear polynomials exactly with just 1 point compared to those 2 points that we used in the trapezoidal rule earlier. So there we have taken the left and the right boundary points, 2 points. But it should be possible from that theory that we choose a single 1 point for integration and still get an exact value for the integral of a linear polynomial. And now you can already guess, well, you can try guessing which point might be interesting here. So that gives us the approach. We want to construct optimal quadrature rules. So we want to construct quadrature rules that for a certain number of points and weights gives us this maximum exactness. So that's what optimality means in this case. So we want for a certain number to have the biggest possible exactness. And in order to derive this, we want to choose points and weights in an optimal way. And for that, we use the monomials, derive equations, and then compute our points and weights in an optimal way. So now let's see how we can derive optimal quadrature rules. We start in 1D with the so-called Gaussian quadrature. So it is named after the famous mathematician. And I want to give a short remark in the beginning. So the classical Gaussian quadrature is defined on the interval from -1 to 1, because that is a bit better in terms of symmetry. But we will here use 0, 1 as an interval. This is better for us because we keep it consistent with the reference for our quadrature. So the reference for the quadrature is supposed to be the same as we use for the FEM, and that's why I won't put the -1 values in here. Also, it's super simple to transform quadrature rules between different intervals, so that's not a big deal. It's just if you look at textbooks or some other pages about classical Gaussian quadrature, you will usually find them defined on the interval -1, 1, and that's no problem. You can just transform it. Okay, let's go. The goal is for a certain number of quadrature points NQ, we want to choose the points and weights in an optimal way such that we reach the exactness 2 NQ -1. And a rough estimation of this, in order to get a feeling why it is possible, well, if you can choose points and weights freely, this gives you 2, in a certain sense, degrees of freedom for every point, because you can choose the value of the point and the value of the weight. So that kind of makes sense. More precisely, we use the points and weights as unknowns for a linear system, and that is precisely 2 times NQ variables. And for each monomial, we use the exact value of the integral to set up the equations, and that's also 2 NQ equations. Why is that? Why does that make sense? Because for the monomials, it's simple to compute the integral. So there we can do an analytic computation of them and use this to derive our equations and then form the optimal quadrature rules. What can we expect? Well, if you use a single 1 point, this gives you exactness 1. That's what we mentioned before. So the improvement of the trapezoidal rule would be to simply define a scheme with 1 point instead of 2. If you choose 2 points, you get an exactness of 3. If you choose 3 points, you get an exactness of 5, and so on. And to make this more precise, we start with an example. So we derive the formula for exactness of order 1. And step 1 is to compute the exact integrals for the monomials up to degree 1. And that in 1D is simply the functions 1 and x, right? That is all monomials up to order 1, because this one here is x to the power of 1. And that's super simple. So the integral of the function 1 from 0 to 1 is simply 1, because it is the width of the interval. And if I integrate the function x, this gives me 1/2 x squared as a primitive, and integrated from 0 to 1, that is 1/2 1 squared minus 0, so that's 1/2. Okay, here you see why it is actually simple. So when you only have to compute the integrals for those monomials, then you can always do that quite simply. And then the second step is we make an ansatz for the number of quadrature points given on or based on the required exactness. And we see that if we want exactness of 1, so integrating linear polynomials exactly, then we should choose nq equal to 1. So we have only 1 point and 1 weight. Meaning that our whole quadrature rules of summing over all points and weights essentially breaks down to simply evaluating your function at a single point and multiplying with a single weight. And now that next step is to put those two things together. So you put these integrals over the monomials together with the ansatz that you made here by saying that, well, I want this here on the left, so I want the integral over monomial 1, which was the value 1 that we just computed. I want this to be equal to the application of my quadrature rule. And if that quadrature rule is w1 times f of x1, and your f is just the constant 1 function, this gives you w1 times 1. And for the other monomial, the function x, the integral value was 1/2. And there we want it also to be equal to the use of the quadrature rule. And there, if f is the function x, you get w1 times x1. So you get this very, very simple linear system. No, that's actually not the system. That is already the result. So the linear system was like this. And then you solve it and you find out that the weight is just 1 and the point is 1/2. So maybe someone has already guessed that it makes sense if you want to get a better approximation. It doesn't make sense to choose the two boundary points of the interval, but instead to choose the middle point. So our whole quadrature rule simply says you can approximate an integral by evaluating that function at the middle point of the interval. And even more, if the function is linear, then this gives you the exact value. Let's try a geometrical interpretation. So if we have a linear function given on the interval from 0 to 1, and we want to integrate this, then this means that we have this function here, and we want to compute the area below this function. And our quadrature rule is given up here by simply saying it can be approximated, or it can be exactly computed in our linear case by the function value at 1/2. Now let's try to do this. If you divide your area into two parts, you have a rectangular part down here and you have a triangular part up here. So the whole area is given as the sum of this triangle part and this rectangle part. And let's try to compute the areas of those individual parts. So this length here is just 1, because it is the interval from 0 to 1. And this length here is given by f of 1, because here is 0 and here is f of 1. Okay, so that whole area of the rectangular part can be given by the value f of 1. Now let's look at the triangular part. And there it's a bit different. There we have to compute the area for the triangle. And how do you do that? Well, for the triangle, you also take the width of your interval. Okay, that again is 1. And this length here is f of 0 minus f of 1, right? So f of 1 is this point here, this value here, and f of 0 is this value here, and that's the length of the side. So if I would draw a rectangle out of this, I would have a tilde of this whole rectangle to be f of 1 minus f of 0. But when we're not interested in a rectangle, we're interested in the triangle, so that's 1/2 times this, and we get to, okay, it's not f of 1 minus f of 0, it's f of 0 minus f of 1, sorry. And then we take 1/2 of this, so we arrive here at f of 0 minus f of 1/2. And that can be expressed in a different way by saying that, okay, well, instead of taking 1/2 of this difference here, I can also evaluate my function in the middle of the interval and subtract the whole f of 1 value. Okay, so that last part is to simply put it together. So a1 plus a2 is f of 1 plus f of 1/2 minus f of 1. So I simply get f of 1/2 as the value. So for this order 1 exact quadrature rule, there is actually a geometrical interpretation, and it also intuitively it makes sense that you have to evaluate your function at the middle or the midpoint of the interval, and that still gives you for linear functions the exact values, because if you know that your function is linear and you know the value in the middle, then you can simply draw those lines in the other directions. Okay? Now let's go to the case of two space dimensions. And there we start with the Gaussian formulas, because it is a very simple thing, which we will see now, to transform those one-dimensional Gaussian formulas to the 2D case. So instead of considering the interval from 0 to 1, we now consider the unit square. So a square from 0 to 1 in both space dimensions. Okay, and we want to derive a quadrature rule that approximates integrals over this omega. And that approach is quite simple. So you take your quadrature rules that you know from 1D and apply them with respect to the x and the y-axis. So you have your x-axis here, and you have your y-axis here, and whatever points and weights you have in 1D, so let's say you have 2 points here with certain weights, then you just draw them on both axes, and then you form the mesh grid out of it, which gives you those this simple formula. So every weight in the 2D case is simply given by multiplying 2 weights from the 1D, and every point is given by combining a 1D point in the x component and a 1D point in the y component. Okay, so meaning that if I have a point here and a point here, I can draw one here, and I can draw one here, and so on. Okay, so if you have one-dimensional points that are optimal, then you can directly transform them to the 2D case. So if you have nq equal 1, the formula that we just derived, then you had the point 1/2 with the weight 1. So your 2D point will be 1/2 and 1/2, and the weight will still be 1. And what does it mean? Well, the most simple optimal quadrature rule in 2D on rectangles is given by taking the midpoint of my square instead of the midpoint of my interval, and the weight is again the number 1. Okay, so that's a direct transfer. If we want to integrate in 2D on rectangles, then it's no problem. Then we can simply take those 1D Gaussian quadrature rules that we have derived and take them into 2D. Now, what happens on triangles? Because honestly, when we define our FEM, we don't really care about rectangles because we're using triangular cells. So what happens if you have to compute integrals on triangles? And here it becomes interesting because that's the thing we actually practically need in our FEM implementation. So how do I integrate over a triangle? Okay, my first guess could be to take those points that we have defined on the rectangles or the square and transform them. But as you can already intuitively guess, transforming from a rectangular or a square shape, so 4 vertices, to a triangle with only 3 vertices, that's gotta be a terrible transformation. And indeed, if you, for example, consider this rule here, this is an exactness of order. So this is with a 2-point rule in 1D that was taken to the 2D with this mesh grid approach that I was just explaining. Now let's say I want to transform this onto a triangle. And what happens is horrible. So just like you see that this transformation in my slides looked terrible, it's also terrible in practical because the distribution of those points inside of our triangle is absolutely not optimal. Those 2 points here are super close to each other. They probably cover almost the same information, and there is this huge area here. So I would say 90% of the triangle is not covered. So all that information that happens here is just not taken care of. So bottom line of this, you cannot just transform those standard Gaussian points onto triangles because otherwise you end up with having a very unoptimal approach. So you would have to take way too many function values to get a very low exactness. But what else can we do? Well, what we do is, instead of taking the actual Gaussian quadrature rules we know from 1D, we only take the approach that was used to compute them. So instead of trying to somehow in a weird way transform the points from rectangles to triangles, we say, okay, what did we do in 1D when we derived those optimal quadrature rules? Well, what we did was we computed the exact integrals for the monomials. We've chosen a required exactness such that the degrees of freedom are matching, and then we have set up a linear system and solved it. And then we were perfectly fine because that gave us points and weights. So no one is stopping us from doing this in the same way also in 2D. So we preserve the concepts and not the results. Let's see. What happens in 2D on a triangle if you want to do a quadrature with nq equal 1? It means that you only take a single point and a single weight, but now that still gives you 3 degrees of freedom in a sense, because you have one weight and the point has an x and a y component. So if you set nq equal to 1, this is in a sense 3 degrees of freedom, because you have one weight and 2 coordinates. Let's look at monomials. And the linear monomial basis, in 1D you only had 1 and x, but now you're in 2D, so you again need the constant. but you also need the function y and not just the function x, because you have one dimension more. So you have one constant function and two linear functions, and this gives you three basis functions. So again, just like in the 1D case, this is a perfect match because you have 3 degrees of freedom and 3 of those monomial basis functions, and that gives you the possibility to set up your linear system. And that's exactly what we're going to do now. So we want to keep in mind that our quadrature rule is supposed to look somewhat like this. And as a first step, we start by computing the integrals for those monomials that we just written down. And keep in mind, t hat is our typical reference cell. So whenever I write t hat, this means that I'm talking about this triangle between 0 and 1. Okay, well, integrating the one function over this triangle is quite simple. I don't have to explain it a lot because the one function always gives you the area. So I can simply say that integral is just the value 1/2, because that's what the area of this triangle is. And now if I want to integrate the function x, I have to make up my minds a little. And this is, in 2D, this integral comes down to, of course, a double integral. And my first integral would be from 0 to 1 with respect to the x-axis. So this integral goes from here in this direction. And let's see, if I have a certain value of x, for example, x is 1/2, then my y values are not allowed to go all the way up to 1, but they are only allowed to go up here because that's where my triangle ends. If my x is going bigger, then I can only go this far up, but only here I can go all the way up. So in a sense that my y on this diagonal line here, y is always roughly 1 minus x. If I'm down here, my x is 0, then my y can be 1. If I'm up here, my x is 1, my y should be 0, and in the middle, and so on. So my second integral is from 0 to 1 minus x hat. And that's an integral dy hat. And with respect to this, I'm integrating the function x hat. Okay, let's see what happens there. Well, if I integrate this function, now this is only a one-dimensional integral. I only integrate with respect to y hat, which doesn't occur in my function. So I can leave the outer integral as it is. And in here, I get a primitive that is x hat times y hat, because with respect to y hat, this was a constant function. So this primitive in the limits from 0 to 1 minus x hat, and I'm left with dx hat. Now I have to insert those values of the boundaries into my primitive. This gives you, I still have an integral from 0 to 1, and I set y equal to 1 minus x hat, and I set y equal to 0. Okay, that part with a 0 just vanishes, and that part with the 1 minus x hat gives you this 1 minus x hat part. Okay, and then I can write this a bit differently, so that's x hat minus x hat square dx hat. And then I can compute this integral as well, and that first part here should give you a primitive of 1 over x hat, 1 over 2 x hat square, and that other part should be 1 over 3 x hat to the power of 3, and those boundaries are 0 and 1. So that 0 part again vanishes completely, and that 1 part is simply 1/2 times 1 minus 1 over 3 times 1. So 1/2 minus 1 over 3, and that is precisely 1 over 6. So my integral over the x is just 1 over 6. Okay, now if I want to do this for the other monomial, then you probably believe me that this turns out to be exactly the same, because you can parameterize this in the other way. So you can again do that same approach and also get 1/6 here as a result for the integral over y hat on the reference cell t hat. Okay, so the first step is done now. We have computed our integrals. And now, just like in 1D, we have to put it together and form our linear system. So we take this approach up here with the 3 unknowns, w1, x1, and y1. We take those 3 integral equations that we have here, and then we put it together. So we want to have that the integral over t hat of the function 1 is integrated exactly. So that is supposed to be w hat. And that's next integral over x hat is supposed to be this way. So this is just the requirements, just like in 1D. That gives you your linear system. And then you can, of course, solve this linear system. So you directly see that w hat 1 is equal to 1/2. And knowing this, you can insert this here, and you see that x1 hat has to be 1/3, and y1 hat is also 1/3. Okay, so again, just like in 1D, you set up your linear system by making an ansatz like this, and then inserting the exact values for the monomials. And this gives you your quadrature rule. And this quadrature rule involves one point with x and y coordinates and one weight here. How does that look? Well, the point 1/3 in x and y components is simply the barycenter of the triangle, and 1/2, and that is not a coincidence, is the area of the triangle. So you will always have the case that the weights sum up to the area of the shape you are considering. So the area of this triangle is 1/2, meaning that every quadrature rule that I define should have weights summing up to 1/2. And now, well, that the barycenter is the important point is also kind of intuitive, because the barycenter is to the triangle what the midpoint is to the interval or the square. So you see that by using this approach, which seems kind of complicated in the beginning, you in the end have points and weights which are quite intuitive, because if I would ask every one of you to choose one relevant point that represents the information of a triangle, you would probably choose the barycenter. Now we can also go to higher orders. I'm not going into details on the computation, but it's done in the exact same way. The only thing is that it is a bit of a bigger system that you have to solve. Here you see that if you want to have exactness of order 2, you need 3 points. And yeah, of course also the weights, the corresponding ones. And looking at this image here on the side, you see that those points again follow a very particular geometrical interpretation. This is also kind of intuitive. Those 3 points are in a sense an optimal spreading of 3 points over the triangle. And then if you go to order 3, you have even one more point. What you also see here is that you have a negative weight here now in the order 3 formula, but you still get the same result that I mentioned before. If you sum all those weights, this gives you 75/96, and this is minus 27/96. So that's 48 over 96, which is exactly 1/2. So no matter how complicated the rule gets, you still have the summation such that it equals the area of the cell. Now, short summary. For the application of FEM, it is necessary to define numerical integration schemes. We've seen that integrals are crucial to this whole scheme. So we need to be able to compute them, and we have also seen that it doesn't really make sense to compute integrals exactly because the whole method is an approximation, so it's not necessary. There exist optimal quadrature schemes that get you the highest possible exactness for a certain number of points. Those are called the Gaussian Quadrature rules. They are usually defined in 1D, but they can easily be transformed into 2D on rectangular domains by simply combining them axis-wise. But for triangular geometry, it's not that simple because you can't just transform them. But what you can do is use an approach like we just did that preserves the idea of computing optimal weights and points while actually doing a different approach with the corresponding monomial basis. And here just at the end a rule of thumb for FEM, because that was the introduction. If you want to know which exactness to choose, a recommendation is to always choose the exactness according to the polynomial degree that you used in your ansatz. So according to your basis functions that you're using in FEM, you should choose the exactness. Why? That's simple. You can simply say that whenever you, let's say, choose a space of piecewise linear functions, then locally every one of those functions is linear. So if I then end up integrating a function phi I over a certain cell and apply my numerical scheme, my quadrature rule to this, then I notice that this is not an approximation, but it can actually integrate our ansatz functions, our basis functions exactly. So this is important here. You can define different types of exactness, and for FEM you should choose the one that matches your polynomial degree.